Imagine a place where gravity is king, a place where the rules of physics as we know them break down, and the very fabric of space and time is twisted and contorted, a place so dense that nothing, not even light, can escape its grasp. This is the realm of the black hole, a cosmic phenomenon that has intrigued scientists and stargazers alike for centuries. This is a black hole, one of the most fascinating and mysterious objects in the universe. Formed from the remnants of massive stars that have ended their life cycles, black holes are regions of space where gravity is so intense that it pulls everything inward, including light. Black holes are not empty spaces but rather regions where gravity is so strong it warps the fabric of space and time. This warping creates a gravitational well so deep that nothing can climb out once it has fallen in. Black holes have captured our imaginations for decades, inspiring countless science fiction stories and movies. From the mysterious monolith in 2001, A Space Odyssey, to the visually stunning black hole in Interstellar, these cosmic giants have been a staple in popular culture. But they are not just figments of our imagination, they are very real and they play a crucial role in the evolution of the universe. Black holes can influence the formation of galaxies, regulate star formation, and even affect the distribution of matter in the cosmos. Their extreme gravity can distort the paths of stars, and they are thought to be the engines behind some of the most energetic phenomena in the cosmos. Quasars, for example, are powered by supermassive black holes at the centers of distant galaxies, emitting more light than entire galaxies. Despite their mysterious nature, we have learned a lot about black holes over the past few decades. Through observations and simulations, scientists have been able to piece together the life cycles of black holes, from their formation to their eventual evaporation through a process known as Hawking radiation. Thanks to advancements in technology and our understanding of the universe, we are now able to detect and study these cosmic behemoths. Instruments like the Event Horizon Telescope have even captured the first ever image of a black hole, providing direct evidence of their existence. And the more we learn, the more we realize how much more there is to discover about these enigmatic objects. Each new discovery opens up more questions, driving us to explore further and deeper into the mysteries of the universe. Black holes are born from the death throes of massive stars. These cosmic giants, which have spent millions of years fusing hydrogen into helium, eventually reach a point where they can no longer sustain this process. When a star much larger than our sun runs out of fuel, it can no longer support itself against its own gravity. The outward pressure from nuclear fusion ceases, and gravity takes over, pulling the star's material inward. The core collapses in on itself, creating a supernova, a spectacular explosion that blasts the outer layers of the star into space. This explosion is one of the most energetic events in the universe, briefly outshining entire galaxies. If the core of the star is massive enough, the collapse continues. The core's material is compressed to extreme densities, and the gravitational forces become overwhelmingly strong. The gravity becomes so intense that it squeezes the core into an infinitely small point called a singularity. This singularity is a region where the laws of physics as we know them break down. This singularity is the heart of a black hole, a point of infinite density and zero volume. It is surrounded by a region where the gravitational pull is so strong that nothing can escape from it. Surrounding the singularity is an invisible boundary called the event horizon. This boundary marks the limit beyond which nothing can return. This is the point of no return for anything that crosses it. Once an object passes the event horizon, it is inevitably drawn towards the singularity. Once something crosses the event horizon, it can never escape the pull of the black hole, not even light. This is why black holes appear black. They trap all light and matter that comes too close. Black holes come in different sizes. The most common are stellar mass black holes, which form from the collapse of massive stars. These black holes have masses that range from a few times to tens of times the mass of our sun. There are also supermassive black holes, which are millions or even billions of times more massive than our sun. These behemoths are found at the centers of most galaxies, including our own Milky Way. How supermassive black holes form is still a mystery. One theory is that they form from the mergers of many smaller black holes. Another theory is that they form from the collapse of giant gas clouds in the early universe. Section 4. Seeing the invisible. Detecting black holes. Black holes are invisible to our telescopes because they don't emit any light. However, we can detect them indirectly by observing their effects on their surroundings. One way is to look for stars that are orbiting an invisible object with a very strong gravitational pull. By studying the orbits of these stars, we can infer the mass of the invisible object and determine if it's a black hole. Another way is to look for X-rays emitted by matter falling into a black hole. As matter falls towards a black hole, it heats up to millions of degrees and emits X-rays that we can detect with space telescopes. Section 5. Time warps and space twists. The effects of black holes. Black holes have profound effects on space and time. These mysterious objects, formed from the remnants of massive stars, possess gravitational pulls so strong that not even light can escape their grasp. This makes them invisible to the naked eye, detectable only through their interaction with surrounding matter and the radiation they emit. According to Einstein's theory of general relativity, gravity is not a force, but rather a curvature of space-time caused by the presence of mass and energy. This revolutionary idea changed our understanding of the universe, showing that massive objects like black holes can warp the very fabric of space and time around them. Black holes, with their immense gravity, create extreme distortions in space-time. This phenomenon, known as gravitational lensing, can bend light from distant stars and galaxies, creating stunning visual effects and allowing us to observe objects that would otherwise be hidden behind them. Time slows down as you get closer to a black hole, and at the event horizon, time stops altogether. This effect, known as time dilation, means that an observer far from the black hole would see events near the event horizon happening in slow motion, while someone close to the black hole would experience time normally. Black holes can also stretch and distort space. This stretching effect, often referred to as spaghettification, occurs because the gravitational pull is much stronger at the black hole's surface than it is further away, causing objects to be stretched into long, thin shapes as they approach. Imagine a bowling ball placed on a rubber sheet. This simple analogy helps us visualize how black holes affect space-time. The bowling ball represents a black hole, and the rubber sheet represents space-time. As the ball sits on the sheet, it creates a depression, similar to how a black hole warps the fabric of space and time. The heavier the bowling ball, the more it distorts the sheet. This illustrates how more massive black holes create greater distortions in spacetime, affecting everything in their vicinity, from light to entire galaxies.